We are looking at finding complex zeros of a polynomial function. We've looked at finding real numbers of a polynomial function, and we looked at some really important theorems that would help us narrow down our search. And one of the best ones was the rational zero theorem. But we're going to use those theorems that we learned the other class period when we're helping us find the complex zeros. So let's just quickly go through the objectives of this section. So hopefully by the end of this lecture, you'll be able to use the conjugate pair theorem to find zeros of a polynomial. You'll be able to find a polynomial function with specific zeros. So given the zeros of the polynomial, we'll be able to find a polynomial function that has those zeros. And then we were going to want to be able to find the complex zeros of a polynomial function. Okay, so in front of us, we're going to have a lot of different definitions and some theorems, and then we'll jump into seeing some examples. So definition of complex zeros. So let's read through the following. A variable in a complex number system is referred to as a complex variable. So a variable in a complex number system is referred to as a complex variable. A complex polynomial function f of degree n is a function of the form. So this just looks just like our polynomial function definition before. F of x equals a sub n, x raised to the nth power, plus a sub n minus 1, x raised to the n minus 1 power, plus dot, 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 plus a sub 2x squared, plus a sub 1x, plus a sub 0. So where a sub n minus 1, a sub 2, a sub 1, and there were other numbers that were excluded. Those are complex numbers. So remember, real numbers are also complex numbers. Remember, our complex numbers were in the form of z equals a plus bi, where a was equal to the real part and b was equal to the imaginary part. And if our b value is 0, then we would have just a real number plus 0 times I. So just a real number. So just keep that in mind, that the real numbers are a subset of that complex number. So if we see a real number there, that is also a complex number. N is a non-negative integer. So we saw that all of our exponents had to be 0, 1, 2, 3, etc. And x is a complex variable. So same as before, a sub n, we say, is called the leading coefficient of f. And the complex number r is called a complex zero if you can plug it back into f, and f of r is equal to 0. So we saw that a real number was a 0 if we could plug it back in wherever we saw an x in our function, and we got back 0. Okay, so I stated down here just what I had stated above and written out. So complex numbers can be written in the form z equals a plus bi. Recall a is the real part, b is the imaginary part. And real numbers are subsets of our complex number system, because b could be 0 in that case. So the fundamental theorem of algebra. So you know that that's going to have to be important, right? Because this is an algebra course. So fundamental theorem of algebra. So the fundamental theorem of algebra states every complex polynomial function f of degree n greater than or equal to 1 has at least one complex zero. So there's a theorem that covers this. So every complex polynomial function f of degree can be factored into n linear factors, not necessarily distinct. So it could have multiplicity. A factor could have more multiplicity greater than 1. And it's going to be in the form f of x equals a sub n, so our leading coefficient. So if that's not 1, we're going to have a sub n out there. x times x minus r sub 1 times the quantity x minus r sub 2 times x minus r sub n, where we say a sub n, r sub 1, r sub 2 r sub n are complex numbers. That is, every complex number polynomial function of degree n greater than or equal to 1 has exactly n complex zeros, some which may repeat. So counting our multiplicity there. So that's pretty kind of strong. If we know we have a degree n bigger than or equal to 1, then we know we have that many complex zeros of that polynomial. And so we are not going to stop searching until we find those. So this next theorem is going to help us when we're looking for our complex zeros. And it's the conjugate pair theorem. So this says, suppose that f is a polynomial function whose coefficients are real numbers. Okay, so this has to state that our coefficients of our polynomial are real numbers. If z equals a plus bi is a zero of our function f, then the complex conjugate z, remember we wrote complex conjugate with a bar over the z bar, is equal to a minus bi, is also a zero. So remember the complex conjugates, we just, or the conjugate, we change the sign in between the real part and our imaginary part. So if we get one of those as a zero, then we know the other one is a zero if the conditions hold. Corollary, so that's like a theorem, but not as strong as a theorem. A corollary states that a polynomial function f of odd degree with real coefficients has at least one real zero. So some of these theorems are, proofs of these theorems are above the scope of this course. They're that theorem that we can factor it into n factors, linear factors. That is proven in the textbook if you want to see that. But we don't have time to go through and prove that, so we're just going to look at some examples. So we have an example in front of us. It's a degree 3 polynomial. We're going to create a degree 3 polynomial that has the zeros 4 and 3 plus I. We're going to find the polynomial f with the given zeros that has real coefficients. And so if we know we have a 0, 4, so remember we can say, well, x equals 4 is a 0, then we could say that, then we know that x minus 4 is a factor. So if x is equal to 3 plus I is 0, then let's subtract 3 and let's subtract I on both sides. Then we know that x minus 3 minus I is a factor. But by the conjugate pair theorem, if 3 plus I is a 0, then we also know that 3 equals, or x equals 3 minus I is also a 0. So let's set that equal to 0 by subtracting 3 and adding I. So we know then that x minus 3 plus I is a factor. So we can get our polynomial f of x. This is equal to our factor of x minus 4, all times our factor of x minus 3 minus I, all times our factor of x minus 3 plus I. So we want to multiply this out. We want to distribute this. I would first multiply through my complex conjugate factors. And when we multiply that through and we simplify, you should not have any more imaginary numbers in there. If you did, then you did something wrong while you were multiplying that out. And so let's just bring down our f of x equals. our x minus 4. And then let's start distributing the complex conjugate factors. So if I distribute my x to each term, I'm going to get x times x is x squared, x times negative 3 is negative 3x, x times I is plus ix. So now let's distribute our negative 3 to each term. So negative 3 times x is negative 3x. Negative 3 times negative 3 gives me positive 9. And negative 3 times I gives me minus 3i. Distributing our negative I to each term, I get negative I times x is negative ix. Negative I times negative 3, that's plus 3i. And negative I times I. So recall I squared was equal to negative 1. So I'm going to have a negative I squared. So negative of negative 1 gives me the plus 1 for negative I squared. So plus 1. Let's close off our parentheses and then let's combine like terms in that parentheses before we distribute. So bringing down f of x equals x minus 4, all times the quantity x squared. So let's combine all of our real coefficients and terms with just an x. So I have a negative 3x minus a 3x. This gives me a minus 6x. Looking at the x terms that have I, we have a ix minus an ix. Those end up canceling with one another. Notice that our complex numbers, negative 3i and positive 3i, those also cancel with one another. And so we're left with the real numbers, positive 9 plus 1. So this is going to give us plus 10. So notice multiplying that out, all of our coefficients of that polynomial that we just got from distributing had real coefficients. So now let's distribute our x. So we have x times x. So this is x cubed. X times negative 6x, so minus 6x squared. And x times positive 10, so plus 10x. Now let's distribute our negative 4. So I have minus 4x squared. Negative 4 times negative 6x, that gives me positive 24x. And negative 4 times 10, so minus 40. So we have here f of x equals, combining like terms, we just have one x cubed term. So let's bring that down. Looking at our terms with an x squared, I have a negative 6x squared minus a 4x squared gives me a minus 10x squared. Looking at our terms that just have x, we have 10x plus 24x, and that gives us 34x. So plus 34x. And then we have minus 40. So that is just one polynomial out of an infinite number of polynomials that has the zeros given that we have. So notice that I could put any coefficient, and we want real coefficients, in front of the factored forms. So I could put any number out here that was a real number, and I would still have those same zeros. And so just be careful if it wants, you know, this or not when you're doing the homework. You might have some stipulation that you can find that coefficient a sub n, so it's a unique polynomial. But what they gave us, they did not give us that information. So we just found one polynomial that has those zeros. So the next example we have is f of x is equal to 3x to the fourth plus 5x cubed plus 25x squared plus 45x minus 18, We're given one of the zeros, and that one zero that we're given is 3i, and we want to find the remaining zeros. And so because they gave us a complex number, 3i is a zero, then by the complex pair theorem, we know that negative 3i must also be a zero. So we can go through, there's a couple ways that we can approach this. So again, we know that negative 3i must also be a zero by the conjugate pair theorem. And there's multiple ways that we can approach this. We can put 3i in our division box and use synthetic division. We know that when we do that, we must get back a zero on that last entry on that horizontal line from the synthetic division because it's a zero bar polynomial. And then we can do the same thing with negative 3i and doing that on the bottom row. The other way that we could approach this is we could multiply the two factors, x minus 3i and x plus 3i together, and use long division to divide that into f of x, and then break down that quotient into linear factors. So either way that we approach this should work. And so let's just, because we were doing synthetic division, let's look at negative 3i. We know that that's a zero. Actually, let's just do the positive one first. Let's do positive 3i. We know that's a zero. We're writing down the coefficients of our polynomial. If there was any term with a missing degree, then we would write a zero there. And so writing down our coefficients, because we're multiplying by a complex number, leave a little more room than we had done in last class period. So we have 3, 5, 25, 45, and negative 18. So with a synthetic division, we brought down our first number, so 3. And then we're multiplying that times the number in the division box. So 3 times 3i, that gives me 9i. So remember, when we're adding real and complex numbers together, we're adding the real parts together and the complex parts together. So 5 plus 0 is 5, and 0i plus 9i gives me plus 9i. So I'm now going to take that and I'm going to multiply that by 3i. And so 3i times 5, that's 15i. We'll put 15i here. And then I have 3i times 9i. Well, 3 times 9 is 27, and I squared is negative 1. So this is going to be negative 27 plus 15i. So adding our real parts, 25 minus 27, that's a negative 2. And then plus 15i. So we're going to have to do a little bit of work on the side. Or I'm going to need to do this on the side just to keep things organized. We're going to multiply 3i now times that negative 2 plus 15i. So 3i times negative 2, that's a negative 6i. I'm going to put negative 6i over here. And 3 times 15, that's 45, but then I have I times I. So 45i squared is a negative 45. So adding our real parts, 45 minus 45 is 0, and 0i minus 6i is negative 6i. And so now 3i times negative 6i. Well, 3 times negative 6 is negative 18. And then we have times I squared, which is negative 1. Negative 18 times negative 1 is 18. And we get a 0 here. So again, we know we need to get a 0 there. And if we didn't, we did some multiplication wrong. We did. So go back and look at it and find it. So now I'm going to go, and I know that negative 3i is also a 0. So I'm going to put that in my division box. I want to break this down into smaller polynomials. So I'm going to use the bottom row of the synthetic division, which I know is that 3 is going to be 3x cubed. That 3 is in front of the x cubed term. So I have 3, then I have 5 plus 9i, I have a negative 2 plus 15i, and then I have a negative 6i. Bring down our first number 3 and distributing, well, negative 3i times 3, that's negative 9i. Summing those up, I would get 5. 5 times negative 3i, that's negative 15i. So summing that row or column up, I get negative 2. Negative 2 times negative 3i gives me 6i. And again, I get a 0 in the last entry, which I know I should get because this is a 0 of the polynomial. So I know the bottom row of the first synthetic division was a cubed, which means the bottom row of that second time we did the synthetic division is a square. And so this is going to be 3x squared plus 5x minus 2. And that's all times x minus 3i, x plus 3i. So this is f of x. And so we want to break down 3x squared plus 5x minus 2. And that's quadratic, so we don't have to use the rules that we did before. We can either use the quadratic formula or see if that's factorable. So I'm just going to try trial and error. Two numbers that would multiply, or two terms that would multiply to give me 3x squared is 3x and x. I'm going to need to make it, so that's, I'm going to do a plus 2 over here, so x plus 2, and a negative 1 here. So negative 1 times 2 is negative 2, so I'm okay with the last term. If we do trial and error, just check to make sure your middle term works out. And so this is a positive 6x minus a 1x, gives us our middle term of 5x, which we wanted. So f of x is equal to 3x minus 1 times the quantity x plus 2 times the quantity x minus 3i times the quantity x plus 3i. And all the zeros are x equals plus or minus 3i. X plus 2 is 0 when x is negative 2. And then we're looking at when is 3x minus 1 equal to 0. So add that 1 and divide by 3 to get x by itself. You would get 1/3. So giving a complex number as a 0, that could help us break it down to find the remaining zeros of the polynomial. So now we have another example in front of us. F of x is equal to x to the 4th plus 2x cubed plus 22x squared plus 50x minus 75. And we're asked to find the zeros of this polynomial. And so we weren't given any zeros of this polynomial. And so we want to, let's look at our rational zero theorem. So our possible rational zeros. So if it's a rational number is a 0, it has to be one of these. We're looking at our p-value. So our p-value or factors of our constant in negative 75. So that could be positive or negative. So numbers that go evenly into 75. So 1 goes into that, 5 goes into that, 15, does 15 go into that? Actually, 3 goes into that. There's a rule that says if you can sum the digits of your number, So 7 plus 5, and that sum is divisible by 3, and then that number of the digits that you summed also has to be divisible by 3. So I know 3 goes in there evenly. 5 goes in there evenly. Well, let's just see. 3 goes into 75. Well, that's 25 times. I don't think 15 goes in there. But let's just check. I don't have the calculator in front of me. That could have been 5. Yep, it does. 15 does go in there. So 15 also goes in there. 25 and 75. Looking at Q were our factors of our leading coefficient, which was 1. So our possible rational zeros were the P divided by Q. Well, if our Q value is 1, when we take every number from P and divide it by 1, we just get back all the numbers from P. So plus or minus 1, 3, 5, 15, 25, and 75. So we could use some of the rules that we looked at last class period. And so if we looked at the possible number of real zeros, positive zeros, we could use Descartes' rule of signs. And this is where we're looking at the number of sign changes in f of x. And so we have a 1x to the fourth to a positive 2x to the fourth. That's no sign change. A 2x cubed to a 22x squared. That's not a sign change. 22 to 50, not a sign change. So 50 to negative 75, that's one sign change. So I know that there is one positive 0. I would subtract that by an even number, but that would give me a negative. And then we could find the possible negative zeros. Possible number of negative real zeros. That's where we would have to look at f of negative x, and we would count the number of sign changes. So going into our polynomial and we're plugging in negative x wherever we see an x, we have negative x to the fourth plus 2 times negative x cubed plus 22 times negative x squared plus 50x, 50 times negative x minus 75. But if you raise negative x raised to the fourth power and you multiply that out, that's going to give you back positive x to the fourth. Negative x quantity cubed is negative and then x cubed. So we can rewrite that next term as minus 2x cubed. Squaring a negative x gives us back positive x squared. So plus 22x squared minus 50x minus 75. So counting the number of sign changes from positive x to the fourth to a negative 2x cubed, that's one sign change. Negative 2x cubed to 22x squared, that's another sign change. 22x squared to negative 50x, that's another sign change. And then negative 50x to negative 75x, that's not a sign change. So counting the possible sign changes there, we have 3 of them. So the possible number of negative real zeros are 3, or if I take that 3 and subtract by an even number 2, 1. So I'm either have 3 or 1 negative real zeros there. And so that can help us narrow down our search. So if we find one real one, positive real one, we could stop and just look for the negatives. And then we can look for our upper bound, lower bound as we're checking numbers. And so let's start out with 1. And we're writing down the coefficients of our polynomial that we're trying to find the zeros of. So 1, 2, 22, 50, and -75. Bring down our first number 1. 1 times 1 is 1. Sum our column. 2 plus 1 is 3. 1 times 3 is 3. 22 plus 3 is 25. 1 times 25 is 25. 50 plus 25 is 75. I was getting excited. Put 75 below, and we have a 0 there. Yay. So we found one real 0, so we could exclude the positives of the rest of them. We know that there's no other one by that Descartes rule signs. And so we know x equals 1 is a 0. We're going to write this as linear factors, so let's just write that we know then that x minus 1 has to be a factor. So now let's look at our negatives. So maybe -1. This bottom row here, I'm going to use this. I know, remember, it was 1 degree less than where we started. And so this was an x to the 4th. So I know this is x cubed plus 3x squared plus 25x plus 75. And I'm just looking at that. I noticed that I could actually factor that without going through and using synthetic division. So let's try factoring that. Notice that there's 4 terms there. Let me just write it down here. And notice that there's 4 terms. Think about trying factoring by grouping, because that sometimes works. And so if we factor by grouping the first 2 terms together and the last 2 terms together. So let's pull out what they have in common for the first 2 terms, which is an x squared. If you pull out an x squared from x cubed plus 3x squared, you're left with an x plus 3. And then notice we have 25x plus 75. So those both have a 25 in common. So we can pull out a positive 25, which is going to leave us with x plus 3, same factor that we had from pulling out the x squared from the first 2. So we can pull out the same factor x plus 3 from both of those groupings. And then you'd be left with the x squared plus 25. So far, we have f of x is equal to the factor of x minus 1 times the factor of x plus 3 times the quadratic factor x squared plus 25. I noticed that x squared plus 25, finding the zeros there. Well, that's not a difference of squares. We can either use a quadratic formula, or we have a perfect square there. We could subtract 25 and then take the square root of both sides. So I got x squared equals -25. Taking the square root of both sides, putting plus or minus in front of the square root that I'm putting the negative under. So I get x is equal to plus or minus square root of a -1 is I. So square root of -25 is plus or minus 5i. So we found all of the zeros. We found that 1 was a 0. Looking at this factor x plus 3 is a 0 when x is -3. And then we also just found that positive 5i and its complex conjugate, -5i, are also zeros. If they wanted you to write it as factors of just linear factors, then we would break down that x squared plus 25 as x minus 5i, x plus 5i. If it wanted you to break it down as factors of linear factors and or irreducible quadratic factors, so meaning those have complex conjugates or complex numbers, imaginary numbers as zeros, then we would leave it as the one above. So it just depends on what the directions are asking you for. We were using information and rules to help us find those zeros of the polynomial that we had learned from the last class period. So I just wanted to state too that noticing this bottom row here, x equals, when we used 1, notice that bottom row was all positive numbers. And if you had a number up here that you were trying that was positive and you get a row of all positive numbers, we know that's an upper bound, meaning that there would be no other number greater than 1 that would be a zero of the polynomial. So if we hadn't thought about our Descartes rule signs, and maybe we remembered that upper bound theorem, that would have told us that we could stop looking for positive numbers and we could just jump in and start looking for the negatives. And so knowing those other rules can be helpful in eliminating, possibilities of trying. But if really the main one that you need to know is that rational zero theorem, because that's what's going to really help us break these down. And then also, if we find one complex number, we know that the conjugate is also going to be a zero, as long as these are real coefficients and not have any imaginary numbers of the polynomial. So now we have another polynomial in front of us. F of x is equal to 2x to the fourth plus x cubed minus 35x squared minus 113x plus 65. And we want to find the zeros of this polynomial, and we want to rewrite this in factored form. And so I would again look at my possible rational zeros to help me break things down if possible. And so factors of 65, 1 goes into it. It's not even, so I know 2 doesn't go into it. 6 plus 5 is 11. That's not divisible by 3, so 3 doesn't go into it. Well, if 2 doesn't go into it, 4 is not going to go into it. I know 5 goes in there because it ends in a 5. Let me just see how many times it goes in there. It goes in there 13 times. So I know the next number that goes in there is 13. And I don't think 15 goes in there. Yeah. So I think the next number is 65 that goes in there evenly. And then looking at our Q values, Q are factors of the leading coefficient, which is 2 in this case. So we have 1 and 2. So if I look at P divided by Q, this gives me positive, negative. 1 divided by 1 is 1. 1 divided by 2 is 1/2. 5 divided by 1 is 5. 5 divided by 2 is 5/2. 13 divided by 1 is 13, and 13 divided by 2 is 13/2. 65 divided by 1 is 65, and 65 divided by 2. So maybe looking at Descartes' rule of signs to help us narrow things down. If we look at the number of sign changes, well, 2x to the fourth to x cubed is not a sign change. X cubed to negative 35x squared is a sign change. negative 35x squared to minus 113x is not a sign change. And negative 113x plus 65 is a sign change. So by this Descartes rule signs, there are two or that number subtracted by 2 is 0, or 0 possible positive real zeros. I can look at what f of negative x is to find the number of sign changes and count and figure out the possible negative zeros. So plugging in negative x wherever I saw an x and simplifying. So negative x to the fourth is like positive x to the fourth. So we have 2x to the fourth left. Negative x quantity cubed is negative x cubed. Then we would have minus 35x squared. Negative x times negative 113 is positive 113x plus 65. So I just plugged in negative x wherever I saw an x and I simplified. So in positive 2x to the fourth to a negative x cubed, that's a sign change. Negative x cubed to a negative 35x squared is not. Negative 35x squared to positive 113x is positive 113x plus 65. So we have two sign changes. So there's 2 or 0 possible negative real zeros by Descartes rule signs. So we know if we find one in either case, there has to be another one by this rule. Okay, so let's go through and start testing. I tend to start with 1 just because it's the easiest. So if I start with 1, again, let's put down our coefficients. There's no missing terms in there, so I don't have to worry about putting 0 as a placeholder. So I have 2, 1, negative 35, negative 113, and 65. Bringing down 2, 1 times 2 is 2, 1 plus 2 is 3, 1 plus 3 is 3, negative 35 plus 3 is negative 32, negative 32 times 1 is negative 32. I can already see here that I'm not going to get 0 at that last entry. So that's what we're looking for. So you might as well just stop. So now let's try 2. Nope, 2 is not one of those numbers. Let's not try 2. How about let's try 5? So 2, 1, negative 35, negative 113, and 65. So bringing down 2, 5 times 2 is 10. 1 plus 10 is 11. 5 times 11 is 55. 55 minus 35 is positive 20. 5 times 20 is 100. Negative 113 plus 100 is negative 13. Negative 13 times 5 is negative 65, and we have a 0. So we're happy we got a 0 here. And so x equals 0. I'm sorry, x equals 5 is a 0, and x minus 5 is the factor. I don't have all positive numbers, so it's possible. I know I have another positive real 0 in there. And so it's possible that it's higher than 5. It's possible that 5 could be it again. So we could technically check 5. And I would use the bottom row that I just simplified and found my 0. So 2, 11, 20, and negative 13. And this polynomial that we just found is degree 3. 1 less than what we started with. So bringing down the 2, 5 times 2 is 10. 11 plus 10 is 21. This is not going to work. 5 times 21 is 105. This gives me 125. And so I know that's not going to work. But I also noticed that those are all positive numbers. And so I know that there's no number higher than 5 that's going to work. So 5 in this case is an upper bound. So I can go back. I noticed that I do have some numbers smaller than 5. I have 1/2 and I have 5/2. I can also look at my bottom row here. And if I looked at the bottom row and did my Descartes rule signs, not Descartes rule signs, if I looked at P divided by Q, 5/2 would not be one of those because 5 doesn't go into 13. So let's try 1/2. So 1/2 up in this upper box. We have 2, 11, 20, and -13. So bringing down our 2. 1/2 times 2 is 1. 12 plus, or 1 plus 11 is 12. 1/2 times 12 is 6. 20 plus 6 is 26. 1/2 times 26 is 13. And that gave me a 0 here. Yay. So I just found another 0 of that polynomial, which is 1/2. We found that there were 2 zeros, so they're positive real zeros. So I know that there's no other positive real zeros there. I can exclude checking anything else. If x equals 1/2, then x minus 1/2 is a factor. Or we can say x equals 1/2, just so we don't have fractions. If we multiply both sides by 2, we get 2x equals 1. And then subtract 1. So I also know x minus 1/2 a factor. We can write that as 2x minus 1 is a factor. So we had started with that as that was a degree 3 in the top. And so 1 less is going to be degree 2. And so this bottom row here, degree 2. So this is 2x squared plus 12x plus 26. I notice that those are all factorable by 2. So let's pull a 2 out of all those terms. We get x squared plus 6x plus 13. I don't see two numbers that multiply to give me 13 and add to 6. And so I would use my quadratic formula on this x squared plus 6x plus 13. And I know x is equal to negative b. So -6 plus or minus the square root of b squared. So 6 squared is 36. Minus 4 times a. So 4 times 1 is 4. Times c, which is 13. So 4 times 13 is 52. All over 2 times a, which is 1. So I notice right here, this is going to give me a complex number as a 0. So -6 plus or minus the square root, 36 minus 52. That is -16 all over 2. So x is equal to -6 plus or minus 4i all over 2. I could divide each term by 2 or rewrite that as 2 separate fractions and simplify. So 2 goes into -6 3 times, plus or minus 2 goes into 4i 2i times. So our zeros are x equals 1/2, x equals 5, x equals -3 plus 2i, and -3 minus 2i. if they wanted us to factor that in linear factors and or irreducible quadratic factors, we would have x minus 5 all times that 2x minus 1 all times x squared plus 6x plus 13. And we can't forget about that 2 in front. Maybe put that out here in the front there. And so here we have it factored into linear and or quadratic irreducible factors. So that those tricks that we learned from the last class period and the last section are also helpful for this section.